Okay, good morning again. This is Professor DavidJDelosReyes. It's August 31. The time is 3:34 a.m. My next topic will be a long video format discussion on alternating current circuit. We are running smooth on alternating current circuit. This will now be lesson number 35. Okay. The title of the topic will be loop equations. Okay. We check the solution loop equations by using Thevenin's theorem to check its validity. So the title is actually loop equations checked by Thevenin's theorem. Okay. Okay, let's proceed. uh, Lesson number 34 was actually an application problem or circuit problem that was solved by using uh, loop equations. And the configuration of the circuit the last time around was this. Okay, so by using the loop equations on lesson number 34, we were able to compute for the current passing through this by using loop equations. Okay, so to check the validity of the loop equation, I will present a Thevenin solution and let us see if the answers will be the same. Okay, let's proceed. I will repeat the figure. This will still be the figure. The given impedances are these, and the voltage sources are this. Voltage source number 1, voltage source number 2. So for this morning, we will be presenting the solution, Thevenin's theorem solution, solving the same problem. Okay, so it seems this is just a backdrop of the Thevenin's topic, but the relevance of this is that we will check if the loop equations was really correct. The answer will be correct. So we will be presenting that the answer for the Thevenin's is the same as for the loop equations. So we can say that our theories are actually correct. Okay, let's proceed. For the Thevenin's theorem solution, step number 1, there's two steps. For Thevenin's theorem, we will, what we call this, compute for the open circuit voltage ETH. Okay, meaning to say we will disconnect the load. Okay, we will disconnect the load. Then we'll try to compute for the voltage across the terminal. Okay, this should be ETH. Okay, the open circuit voltage for Thevenin's theorem. Okay, so if we try to disconnect the load, the configuration will be this. Okay, so it seems this is gone. Right, so it seems we are just having two generators connected in parallel, okay, giving off a current. There will be a current due to this, and there will be a current due to this, and what will be the circulating current? And the formula on how to compute for the circulating current is the net voltage on the circuit considering the IC loop. Okay, considering the IC loop, the net voltage will be the difference E1 minus E2. It should be minus because their polarities are actually opposite, right? This is minus to plus, and when the circulating current passes through the source number 2, it should be from plus to minus, so this is minus. So the operation is minus, right? They don't add up because they are in opposite direction, right? So it will be the bigger minus the smaller, it depends. So I place it here. With this given configuration, circuit tracing, it should be E1 minus E2. And if we try to compute for E1 minus E2, I think the last time around for lesson number 34, we computed already E1 minus E2. The difference is 64.716. Angle negative 73.16 degrees. Okay, I will not show you any more the solution of this one because it was given on lesson number 34. So we are just continuing lesson number 34. So we will be needing some values coming from lesson number 34. We are solving the same problem. The total impedance after the disconnection, the total impedance is just C1 and C2. So it will be C1 plus C2. We have done this one also from previous lesson number 34, and I think the total sum of C1 and C2 in terms of polar is 1.388 angle 36.41 degrees. Okay. So we are given the voltage on the loop, we are given the total impedance on the loop, and by using the equation voltage equal to IC, okay, considering the loop after the disconnection, okay, the circulating current will be equal to voltage over Z. And this voltage here is actually the difference E1 minus E2. Okay, and this Z here is actually the sum C1 plus C2. Right? So the circulating current after the disconnection will be the ratio 64.716 over 1.38. What will come out will be 46.625. The angle will be, what will be the angle? A minus and a minus, so it will add up, right? Negative 110.03 degree amperes. So after the disconnection of C sub L, the circulating current within the system is 46.625 amperes. Okay? Let's try to compute for ETH. For ETH. I will try to remove this one so it will look good. Right? Considering the right loop is this one. Right? Take the summation of the voltages. Okay? This will be our voltage source minus to plus, so this is plus E2. Okay? The circulating current originally was like this, right? This is the circulating current originally. Okay? So it will be plus IC times C sub 2. The voltage drop across C2 due to the circulating current is the product IC times C2. This is plus IC times C2. Okay? And the voltage across this is actually ETH. It should be a minus, it's a voltage drop, and this should be equal to 0. Computing for ETH, so it seems we still use the loop equation, right? Taking the summation of the voltages here to get the relation of ETH with respect to the parameters on the right loop. So if we try to compute for ETH will be, we'll just transpose this on the right and we rearrange. It will be E2 plus the product of circulating current times C sub 2. That's why we have computed I sub C a while ago. That's the importance, because in the computation of the open circuit Thevenin's voltage, we need I sub C. Okay? Because if we try to multiply IC times C2, it will be the voltage drop across this. Okay? So, performing this operation here, okay, I will not go into detail already. Some parts were shown on from the previous example. What will come out for ETH, meaning the Thevenin's open circuit voltage, is 239.587 angle 66.08 degree volts. So, I will try to reach it. ETH here is that value, right, across this. What's next? For Thevenin's theorem, after computing for the open circuit voltage, we will compute for the open circuit impedance. Meaning to say, you try to short out voltage source number 2 and number 1, so what remains inside will just be simply the internal impedance number 1 and number 2, so we could compute for CTH, right? After the shorting of, that's the procedure, right? You remove E2 and E1, but place their internal impedances, so we could compute for the open circuit impedance over here. And if you try to see it, they are in parallel with respect to this, right? So it should be the product over the sum. Right? That one emanates from 1 over CTH for parallel equal to 1 over C1 plus 1 over C2. And if we try to simplify this one, it will be this. Okay? So it's just a matter of substitution. C1 given, C2 given. The sum C1 plus C2 is actually this one. Where is it? 1.38, 36.41. So the bottom portion is 1.38, 36.41 degrees. So the open circuit impedance, okay, I will just give you the rectangular equivalent now. Some other operation were performed from the previous example, so this should be 0.2703 plus J 0.2157 ohms. Or the last step, we must have to draw the Thevenin's equivalent, and under Thevenin's, the open circuit voltage is in series with the open circuit impedance, and C sub L is connected across it. So this is the open circuit voltage. We have computed by using step number 1. It's this. And that open circuit voltage is connected in series with the Thevenin's open circuit impedance. In series, right? So for Thevenin's, it is in series. We have computed this one. Then we try to reconnect. This is the point of connection, right? We reconnect C sub L. So after the reconnection of C sub L, we could say that CTH and C sub L are in series. So to compute for I sub L now, it will be this voltage here plus the vector sum of CTH plus C sub L. That's why I place here CTH, Thevenin's open circuit voltage plus the load impedance, this. Simplifying, the magnitude will be 14.766 angle 33.8 degree ohms. Okay, and again, using the equation voltage equal to IC, current now will be equal to voltage over Z, and this voltage here is the open circuit voltage, and this here is actually the sum of CTH plus CL. Okay, we are given these two values here, plus this value, that's the per ATH, this is CTH plus CL. So IL now will be 239 over 14.766. Take the angle, okay? 6.08 over 33.8. 239 divided by this is 16.225. Okay. I will try to show you so you believe in the solution. 239.587. We are divided by 14.766 equals, okay, 16.225. Okay, and the angle will be 6.08. We raise this up. Okay, so it will be negative. The angle is negative 27.72 degree. The unit is amperes. How do we know if this answer is correct? From the previous solution, loop equations are current. That's why I wrote it here. The current that brought out using the loop equations is 16.225, angle negative 27.73 degree amperes, using the loop equation. Because our topic for tonight is that we are checking the loop equation solution by using Thevenin's theorem. And what comes out for Thevenin's theorem, it's the same. 16.225, angle negative 27.72 degree amperes. Hallelujah. Okay? Both the loop equations and Thevenin's theorem solution are very good. We are in good standing. Okay, that's it, guys. That's our topic for tonight. So for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/ProfDavidJDelosReyes. If you want to share it, please click share. Try to watch my long video format discussion on alternating current circuit. I will assure you, you will learn something from it. Okay, good morning from Los Angeles, Professor David J. Delos Reyes.